Introduction and Problem Definition. Welcome to this deep dive into building a visual search system using machine learning. Today, we're going to explore how companies like Pinterest, Google Images, and e-commerce platforms enable users to search for images using other images. So, what exactly is visual search? Imagine you're browsing online and you see a beautiful chair you love. Instead of trying to describe it in words, you simply upload a photo and the system returns similar chairs from across the platform. That's visual search in action. The core problem we're solving is this. Given a query image from a user, we need to accurately retrieve images that are visually similar and rank them by their similarity. This technology powers product discovery in e-commerce, content platforms like Pinterest, fashion apps, and countless other applications. Now, let's dive into how we build such a system using machine learning. Framing the ML problem. The first crucial step in any ML system design is framing the problem correctly. We need to transform our business problem into a well-defined machine learning objective. Our ML objective is straightforward. Accurately retrieve images that are visually similar to the user's query image. The system takes a query image as input and outputs a ranked list of similar images, where more similar images appear higher in the results. This is the key insight. Visual search is fundamentally a ranking problem. We're not just finding similar images, we're ordering them by relevance. This is the same category of problems that includes recommendation systems, search engines, and document retrieval. But how do we actually solve this ranking problem? This is where representation learning comes in, and it's one of the most powerful techniques in modern machine learning. In representation learning, we train a model to transform images into numerical representations called embeddings. Think of it this way. Instead of working with raw pixels, we map each image to a point in a high-dimensional space. Let's call it the embedding space. The magic happens because of how we train this model. Similar images are mapped to points that are close together in this space, while dissimilar images end up far apart. So finding similar images becomes a geometric problem. We just need to find the nearest neighbors to our query point in this space. How ranking works. Let's break down how we actually rank images using this approach. It's a three-step process. First, we generate embeddings. We pass all images in our database through the trained model, and each image becomes an embedding vector, essentially a list of numbers that represents that image. Second, we calculate similarity. When a user submits a query image, we generate its embedding and then measure the distances between this query embedding and all other embeddings in our database. We typically use metrics like dot product or cosine similarity for this. Third, we rank and return results. We sort all images by their similarity scores and return the top K most similar images to the user. The beauty of this approach is that once we've pre-computed embeddings for all images in our database, searching becomes incredibly fast. It's just a nearest neighbor search problem. Data preparation. Now let's talk about data. What data do we need to build the system? We have three main data sources. First, we have the images themselves, uploaded by creators to our platform. Each image comes with metadata, things like owner ID, upload time, and manual tags like zebra or pasta or family party. Second, we have user data, demographics like age, gender, location, and contact information. This helps us understand our user base and potentially personalize results. Third, and critically important, we have user image interaction data. This includes impressions, which images were shown to users, and clicks, which users actually engaged with. This interaction data is gold for training and evaluation, as we'll see later. But before we can feed images to our model, we need to pre-process them. Neural networks are picky. They need standardized inputs. So we perform several transformations. We resize all images to fixed dimensions, typically something like 224 by 224 pixels. We scale pixel values to a standard range, usually between 0 and 1. We might apply z-score normalization to ensure the data has a mean of 0 and variance of 1. And we ensure color consistency. All images should use the same color mode, typically RGB. These pre-processing steps might seem mundane, but they're absolutely critical for model performance. Feed a neural network inconsistent inputs, and you'll get inconsistent results. Model development. So why do we use neural networks for this task? Two main reasons. First, neural networks excel at handling unstructured data like images and text. They can automatically learn complex patterns that would be nearly impossible to hand engineer. And second, and this is crucial for our approach, neural networks can produce the embeddings we need. Traditional machine learning models simply can't do this effectively. They weren't designed for representation learning. When it comes to architecture, we have proven options. CNN-based architectures like ResNet have been the workhorses of computer vision for years. More recently, transformer-based architectures like Vision Transformer have shown impressive results, especially when trained on large datasets. The architecture itself is relatively straightforward. We have an input layer that accepts our pre-processed image. Then we have convolutional layers that extract visual features, things like edges, textures, and shapes at various scales. These features flow through fully connected layers that transform them into our final output, an embedding vector in n-dimensional space. The exact configuration, number of convolutional layers, neurons in fully connected layers, and size of the embedding vector, these are all hyperparameters we tune through experimentation. Training strategy. Now we get to the heart of the system, training. How do we actually teach a model to create good embeddings? The answer is contrastive learning. The core idea is beautifully simple. We teach the model to distinguish between similar and dissimilar images. During training, we show the model a query image, one image that's similar to it, we call this the positive image, and several images that are dissimilar. These are negative images. The model learns to produce embeddings where the positive image is close to the query image and the negative images are far away. So finding similar images becomes a geometric problem. We just need to find the nearest neighbors to our query point in this space. Each training example contains one query image, one positive image similar to the query, and n-1 negative images that are dissimilar. The ground truth label is simply the index of the positive image among all the candidates. But here's the million-dollar question. How do we get these positive and negative image pairs? We have three options, each with significant trade-offs. Option 1 is human judgment. We hire human annotators to manually find similar images. This gives us high-quality data, but it's expensive, time-consuming, and doesn't scale to billions of images. Option 2 is using click data as a proxy for similarity. When a user clicks on an image after seeing a query, we assume the clicked image is similar. This is automated and scalable, but the signal is noisy. Users sometimes click on images even when they're not truly similar. Plus, click data is sparse. We won't have clicks for most image pairs. Option 3, and this is what we'll recommend, is self-supervision through data augmentation. We artificially create similar images by augmenting the query image, rotating it, cropping it, adjusting colors or brightness. The augmented image becomes our positive example. This approach is fully automated with zero upfront cost. It's not noisy like click data because an augmented image is genuinely similar to the original. Frameworks like SimClar and Moco have shown this works remarkably well with large datasets. The main drawback is that augmented images aren't quite the same as real-world similar images, but in practice, this works surprisingly well. Of course, we don't have to commit to one approach forever. We might start with self-supervision and later incorporate click data or even combine multiple approaches as the system matures. Loss function. Once we have our training data, we need a loss function to guide the learning process. The goal is to optimize the model so similar images have embeddings close together in the embedding space. Contrastive loss functions work in 3 steps. First, we compute similarities between the query image and all other images in the training example. We typically use dot product or cosine similarity. These work well in high dimensions. We avoid Euclidean distance because it suffers from the curse of dimensionality. Second, we apply a softmax function over these similarities. This converts our similarity scores into probabilities that sum to 1. Third, we calculate cross-entropy loss. This measures how close our predicted probabilities are to the ground truth labels. When the model assigns high probability to the correct positive image, the loss is low. When it's confused and assigns high probability to negative images, the loss is high. By minimizing this loss over many training iterations, the model learns to create an embedding space with the properties we want. One more thing worth mentioning is we don't always have to train from scratch. Pre-trained models that have already been trained on massive datasets like ImageNet have learned excellent visual representations. We can fine-tune these models on our specific data, which dramatically reduces training time and often improves performance. Evaluation metrics and THRI. Evaluation metrics. After training, we need to evaluate our model. Let's start with offline metrics. These are computed on a held-out evaluation dataset before we deploy to users. For evaluation, we assume we have a dataset where each query image has several candidate images, and each candidate has a similarity score, let's say from 0 to 5, where 0 means completely
Want to return all of them, just the most similar ones. Precision at K measures what proportion of our top K results are actually relevant. This is better, but it doesn't consider ranking order. Whether we put the best result first or last, precision stays the same. Mean average precision, or MAP, is an improvement. It computes average precision for each query by averaging precision at different cutoff points, then averages across all queries. This does consider ranking quality, but it's designed for binary relevance. Items are either relevant or not relevant. For our use case, where we have continuous similarity scores, the best metric is normalized discounted cumulative gain, or NDCG. This is the gold standard for ranking problems with graded relevance. Here's how it works. First, we compute discounted cumulative gain, or DCG. We sum up the relevant scores of items in our ranked list, but we discount items that appear lower in the ranking. The formula is sum of relevant score divided by log base 2 of position plus 1. Items at the top contribute more to the score than items at the bottom. Next, we compute IDCG. That's the DCG of the ideal ranking, where items are perfectly ordered by relevance. Finally, we normalize by dividing DCG by IDCG. This gives us a score between 0 and 1, where 1 means perfect ranking. For example, if our model produces a DCG of 6.151 and the ideal ranking has an IDCG of 8.95, our NDCG is 0.69. This tells us we're capturing about 69% of the maximum possible ranking quality. Now let's talk about online metrics. These measure real-world performance after deployment. Click-through rate, or CTR, shows how often users click on displayed images. It's calculated as the number of clicked images divided by total suggested images. Higher CTR generally indicates more relevant results. We also track engagement metrics like average time spent on suggested images, measured daily, weekly, and monthly. When the system is accurate, users spend more time exploring the results. These metrics give us a holistic view of system quality beyond just clicks. Serving architecture. Now let's discuss how this system works in production. We have two main pipelines: the prediction pipeline that handles real-time user queries and the indexing pipeline that processes images offline. Let's start with the prediction pipeline. When a user submits a query image, it first goes to the embedding generation service. This service pre-processes the image, remember all those transformations we discussed, and runs it through our trained model to produce an embedding vector. Next, this query embedding goes to the nearest neighbor service. This is where the magic happens. We need to find images in our database whose embeddings are closest to the query embedding. This is a classic nearest neighbor search problem, but at scale. We might be searching through billions of images. Finally, the candidate similar images go through a re-ranking service. This is where we apply business logic and policies. We filter out inappropriate content, remove private images that shouldn't be shown publicly, eliminate duplicates or near duplicates, and apply any other business rules before showing results to users. The indexing pipeline runs offline and continuously. The indexing service processes all images on the platform, generating and storing their embeddings in an index table. This index is what enables fast nearest neighbor search. Whenever creators upload new images to the platform, the indexing service processes them and updates the index so they become discoverable. One important consideration is memory usage. Storing embeddings for billions of images takes substantial memory. We can use techniques like vector quantization or product quantization to compress embeddings, trading a small amount of accuracy for significant memory savings. Nearest neighbor search. Let's dive deeper into nearest neighbor search because it's absolutely critical to system performance. Even a small improvement in search efficiency translates to massive gains at scale. There are two approaches: exact and approximate nearest neighbor search. Exact nearest neighbor search, also called linear search, is straightforward. We literally compute the distance from the query point to every single point in our index and return the k nearest ones. The time complexity is O of n times d, where n is the number of points and d is the dimension. When n is in the billions, this is far too slow for real-time search. This is where approximate nearest neighbor search, or ANN algorithms, come in. The insight is that we don't always need the exact nearest neighbors. Neighbors that are close enough are usually sufficient. ANN algorithms use clever data structures to reduce time complexity to something sublinear, like O of d times log n. There are three main categories of ANN algorithms. Tree-based methods like R-trees, KD trees, and Denoy partition the space into a tree structure. Then they only search the partition that contains the query point. Locality-sensitive hashing, or LHS, uses special hash functions that map nearby points to the same bucket. We only search points in the same bucket as our query. Clustering-based methods group similar points into clusters. We only search within the cluster that contains our query point. For our visual search system with billions of images, ANN is the practical choice. We give up perfect accuracy for dramatic speed improvements, and in practice, the results are more than good enough. If you're implementing this system, I recommend getting familiar with libraries like Feist from Meta or Scan from Google. These implement most ANN algorithms and are battle-tested at massive scale. Advanced topics. If we have time, let's touch on some advanced topics that take the system to the next level. Content moderation is critical. We need to identify and block inappropriate images before they appear in search results. This protects users and the platform. Bias is another important consideration. Systems often exhibit positional bias. Users are more likely to click on items at the top of the results, regardless of actual relevance. We need to account for this when interpreting click data. We can enhance results by incorporating image metadata like tags. Combining visual similarity with textual information often produces better results than either signal alone. For product images, smart cropping using object detection can automatically focus on the main subject, improving thumbnail quality and user experience. Graph neural networks offer a way to learn even better representations by leveraging relationships between images, things like which images appear together or are uploaded by the same creator. Looking toward the future, we might want to support text-to-image search, where users can search with descriptions instead of images. This requires multimodal models that understand both vision and language. Finally, active learning and human-in-the-loop approaches can help us annotate data more efficiently, focusing human effort where it's most valuable for improving the model. Conclusion and key takeaways. Let's wrap up with the key takeaways from building a visual search system. First, problem framing is crucial. We framed visual search as a ranking problem and chose representation learning as our solution approach. Images are transformed into embeddings in a space where similarity is preserved geometrically. Once we have good embeddings, the rest becomes engineering: efficient indexing, fast nearest neighbor search, and thoughtful re-ranking. Throughout the system, we're constantly balancing trade-offs: accuracy versus speed, exact versus approximate search, manual versus automated labeling. There's rarely one perfect solution. Success comes from understanding these trade-offs and making informed decisions based on your specific requirements and constraints. If you're interviewing for ML roles, remember that interviewers are looking for several things. Can you frame problems correctly as ML tasks? Do you understand the technical depth, things like representation learning, evaluation metrics, and serving architecture? Can you discuss trade-offs thoughtfully? And perhaps most importantly, do you think practically about scalability, real-world constraints, and iterative improvement? Building a visual search system is a fascinating challenge that combines computer vision, information retrieval, and large-scale system design. The techniques we've discussed today, representation learning, contrastive training, approximate nearest neighbor search, and ranking evaluation, these are fundamental building blocks that appear across many ML applications, from recommendation systems to document retrieval and similarity search in countless domains. The key insight to remember is that we transformed a seemingly complex problem, finding visually similar images, to an elegant geometric problem in embedding space. Once we have good embeddings, the rest becomes engineering: efficient indexing, fast nearest neighbor search, and thoughtful re-ranking. Interview preparation tips.
Before we close, let me share some advice for those preparing for ML system design interviews on this topic. First, always start by clarifying requirements. What does similar mean in this context? What scale are we talking about? Millions or billions of images? What are the latency requirements? Understanding constraints up front helps you make better design decisions. Second, discuss multiple approaches and their trade-offs. Don't just jump to one solution. For example, when talking about creating training data, explain all three options: human annotation, click data, and self-supervision, and justify why you choose one over the others given specific constraints. Third, show depth where it matters. You don't need to memorize every detail of every algorithm, but you should understand core concepts deeply. For instance, know why we use contrastive learning, how loss functions guide training, and why approximate nearest neighbor search is necessary at scale. Fourth, think end-to-end. Don't just focus on the model. Consider data collection, feature engineering, training infrastructure, evaluation, serving architecture, and monitoring. Production ML systems are about much more than just the algorithm. Finally, demonstrate practical thinking. Talk about how you'd start simple and iterate. Maybe begin with self-supervised learning, monitor performance, and add click data later if needed. Discuss how you'd A/B test changes. Consider failure modes and how you'd handle them. Real-world considerations. Let me also touch on some real-world considerations that separate good systems from great ones. Latency matters
tremendously. Users expect search results almost instantly. This means you need to carefully optimize every component, from embedding veneration to nearest neighbor search to re-ranking. Even saving 50 milliseconds can significantly improve user experience. Quality and diversity both matter. You want similar images, but you also want diverse results. If someone searches for a red chair, they probably want to see different styles of red chairs, not 20 variations of the exact same chair. Cold start is a real challenge. What do you do with brand new images that have no interaction data? How do you surface them in search results so they get initial exposure? Continuous learning is essential. Visual trends change. New products are added. User preferences evolve. Your system needs to adapt. This might mean periodically retraining your model, updating your index, or adjusting your re-ranking logic. Cost optimization is often overlooked in interviews, but critical in production. Storing and searching billions of embeddings is expensive. Techniques like quantization, caching popular queries, and smart index partitioning can dramatically reduce costs while maintaining quality. Closing thoughts, 30 seconds. Visual search is one of those magical ML applications that feels like the future. Natural, intuitive, and powerful. Behind that magic is a carefully designed system balancing multiple components: smart representation learning, efficient indexing, fast retrieval, and thoughtful business logic. Whether you're building this for e-commerce, content discovery, or any other application, the principles we've covered today provide a solid foundation. Start with a clear problem formulation, choose appropriate techniques, evaluate rigorously, and design for scale from day one. I hope this deep dive has given you both the conceptual understanding and practical insights to tackle visual search problems, whether in an interview setting or in production. The techniques we've discussed, representation learning, contrastive training, approximate nearest neighbors search, and ranking evaluation, these are fundamental tools in the modern ML engineer's toolkit that extend far beyond just visual search. Thank you for joining me on this journey through visual search systems. If you found this helpful and want to dive deeper into ML system design, there are excellent resources available. Check out frameworks like SimCLR and Moco for contrastive learning, experiment with libraries like FOSSIS and ScanN for nearest neighbors search, and most importantly, get hands-on experience building and deploying these systems. Now go out there and build amazing search experiences. Good luck and happy learning!